Welcome back. This video is going to cover seasonal ARIMA models. This is the fifth and last video on our chapter that covers ARIMA models. Make sure you've watched the previous 4 videos if you haven't already done so, otherwise this video is not going to make a lot of sense. So in the previous video we talked about ARIMA models. They don't work if you have a strong seasonal pattern. That's why we would need one of these seasonal ARIMA models that I'm going to talk about here. So as always, I'm going to use the variable m to denote the length of the seasonal period. So if we have quarterly data, m is going to be 4. If we have monthly data, m would be 12, and so forth. So the basic idea of a seasonal ARIMA model is that we're going to have seasonal differences rather than just first order or second order differences. So this could be a difference of order m. Then what we're going to do is include seasonal autoregressive terms. So y sub t could depend on y sub t minus m. So in other words, first quarter this year could be predicted by first quarter last year. We'll also include a seasonal moving average. So my sales first quarter this year could depend on the air from first quarter last year. The notation that we're going to use is to use lowercase letters for normal ARIMA, uppercase letters for the seasonal part. We'll write out a seasonal ARIMA model followed by 2 triples to specify the model. This would say we're going to have a normal ARIMA model with P autoregressive terms, D differences, and Q moving average terms. Then big P is going to be the number of seasonal autoregressive terms, big Q will be the number of seasonal moving average terms, and big D will be the number of seasonal differences that we include. One more thing. Back with basic ARIMA models, we used little phi to indicate the parameters for the autoregressive terms and little theta for the moving average parameters. For seasonal ARIMA, we're going to use a capital phi, which is written as follows, for all of our seasonal autoregressive parameters, and we're going to use big thetas to indicate our seasonal moving average parameters. Let's take a look at an example. So the example I have is a 111 sub 4 model. So the 4 is the seasonal period. So we've got quarterly data. We want one difference, one seasonal difference, one moving average term, one autoregressive term and one moving average term, one seasonal autoregressive term, and one seasonal moving average term. Perhaps the easiest way to write this is in differenced notation. This specifies that we want an autoregressive term of order 1. This term says go back 4 periods to give us a seasonal autoregressive term. We want a difference, so that difference is because of that 1 right there. We also want seasonal differences, so take the current y minus what happened 4 periods ago. That's indicated by this 1 right here. We also said we want a normal moving average and a seasonal moving average term. So here's the normal moving average term. That matches up with this 1. The seasonal moving average term matches up with this 1. If you multiply this out, so it's going to be slightly tedious, I've left it as a your turn for you, and then collect all the terms, you end up with the following expression for yt. So I'd encourage you to try this. It's slightly tedious, but it will test your understanding of this backshift notation. A couple more things about this. In my ARIMA 111 model, I did not add subscripts. So the textbook would add a sub 1 to all the little phis, all the big phis, all the little thetas, and all the big thetas. Since there's only one of each of these, I omitted the subscripts. If you have more than one, as we did with ARIMA, we'll just add some subscripts. I will mention, at least on the seasonal side, it's rare to have more than one autoregressive term and rare to have more than one moving average term in there. Typically, if you're going to do some sort of seasonal model, you'll do one seasonal difference. It's possible to have other configurations. We can use ARIMA, and it may choose something slightly different than what I'm specifying, but these are the things that tend to come up. I'd now like to go over the Amazon model again that we've been using throughout the class, and I'd like to kind of start with where we left off in the Holt-Winters lecture. So as a little review, let's go take a look at the plot. So to get started, let's go look at the time plot. And so as we've seen many times before, we see exponential growth with the amplitude of the seasonal effects growing over time, signaling we're going to need a multiplicative model. What we learned back in the Holt-Winters section was a log transform does a pretty good job of fixing the exponential growth and the changing amplitude of the seasonal effects. If we go look at the time plot, we see that the exponential growth has become a linear trend in log space. So that's a nice thing. Maybe the amplitudes have flattened out a little bit. We mentioned that before. When I look at the ACF, what I see is a couple things. So first off, the ACF decreases kind of geometrically, suggesting we need an autoregressive function. When I look at my PACF, what you'll see is strong periodicity. You'll notice we have a giant spike at 1 lag, and then we have an almost significant spike at 4 lags. I'm somewhat surprised that isn't significant. Very often with seasonal data, you'll get spikes every M periods. We then see a negative correlation if we go 5 periods out, and this pattern repeats. So you get 3 small values, then a big negative value, and that repeats, really signaling we definitely have some seasonal data. Now, remember when I talked about differencing, I said we usually take seasonal differences first, and sometimes that's all you need. You don't need to do first order differences after you've done your seasonal differences. So let's go make a time series plot with lags of order 4. And so what we now see is the seasonality's been removed. I see some definite wandering, like there's some autocorrelations that need to be taken care of. When we go look at our PACF, we see a giant spike. Then we see a negative correlation that's actually borderline significant. What this is telling me is we need at least one autoregressive term, maybe a moving average term, but we'll have to see. The Amazon data is a very nice long time series. As I did in the Holt-Winters video, let's set aside the last 5 years as the test set. Now we're only going to use data through the first period in 2015 to train our models. We use the rest for the test set. Back in the Holt-Winters lecture, we decided that an additive model using the log data gave a very good fit. If we look at the parameter estimates, what we see is that we give about 17% of the weight to the most recent value when computing the level. The slopes is pretty much constant over the entire range. So that very small beta value means we're giving about the same amount of weight for all changes in slope. The gamma of 0.6 is saying give a lot of weight to the most recent seasonal effect, less weight to previous ones. We generated a plot in the previous lecture that looks something like this, showing that we do a very good job of fitting the data, and when we forecast into the future, we're doing a very good job as well. So those last 5 years, we're kind of nailing. So that's a good model. It'd be a tough model to beat, to be honest. Let's just let ARIMA do its thing now and see what it comes back. So ARIMA chooses a model that has an autoregressive term, a moving average term, and no first order differences. Then it wants two autoregressive seasonal effects, seasonal differences, and no moving averages. Here are the estimated parameters. We could go write out exactly what this model is. So I wrote out what the parameter estimates are here ahead of time. Let's go write out the model. So remember, we've got seasonal differences. So what that says is y sub t minus y t minus 4. That's our seasonal difference, is equal to, well, we've got a constant, so that's our called the drift constant. Then what we have is our first order autoregressive coefficient, so 0.73 times y t minus 1. Let's put all of our terms together. Minus 0.38 times, this is going to be y t minus 1 minus y t minus 5. So think of this as the lagged seasonal difference. Then let's do the next one. Minus 0.32. This is going to be 2 periods lagged. So y t minus 2 minus y t minus 3. Then what we have is plus 0.42 epsilon hat t minus 1 plus epsilon sub t. And our epsilon t's are distributed normally independent of each other, mean 0, and the variance is 0.001. So that's the model that we've come up with. I kind of like parsimonious models. Do we really need these two seasonal autoregressive terms? I'm going to get rid of them. Let's just see how we do without those. We'll keep the drift term, but now notice those two seasonal effects went away. If we compare the two models, the corrected AIC is about minus 145. The previous one was minus 146. So there's not a lot of difference. You want AIC to be small. The model that ARIMA chose is a little bit better than the more parsimonious model that I chose, but I'm not sure it's worth. The difference is pretty small. That's a judgment call that we'd have to make. We could go look at some plots to see how they compare. So here's the plot. What we see is that the models are all pretty good. Here are the forecast values. It looks like the green one that ARIMA chose with two seasonal autoregressive terms may be a little bit higher than the others, but there's not much of a difference. Another way to evaluate these is to look at the accuracy on the test set. So let's go do that. So I've generated these, and what we see is that there's not a lot of difference in the RMSE values in the test set. So this is the Holt model, 78.73. The ARIMA model is also 48.73, slightly larger in the third decimal place. You can see that my more parsimonious model is 48.77, so just a tiny bit worse than the ARIMA model. When we look at the other measures, we come to similar conclusions, that the Holt-Winters estimates win by a tiny bit. The other models are pretty close. Okay, I'd now like to talk about the relationship between ETS and ARIMA models. So there's a myth out there that ARIMA models are more general than exponential smoothing models. The myth is that all exponential smoothing models are really just special cases of ARIMA, and ARIMA does other models, and therefore we should just use ARIMA. But that's not quite true. So it is true that many linear exponential smoothing models are special cases of ETS models. So I've listed below how various ETS models are related to ARIMA models, but what you'll notice is that none of the multiplicative models are listed here. So there are no equivalent ARIMA counterparts for those nonlinear exponential smoothing models. I'm not going to take a side in this argument, but I'd like to suggest that whenever you have an important forecasting problem, you consider both. and then make your final selection based on which model is more theoretically plausible and which one does better on the test set. So I think there's a lot of value in looking at both approaches.